Hey there, welcome to video 19. Today we're going to look at collector feedback biasing. Collector feedback biasing is a pretty simple biasing arrangement. It only requires two resistors. It's not especially beta independent, but it has a couple of nice characteristics that we'll see in a few minutes. All right, let's start here by doing the easy stuff first. Let's find VCE cutoff, which by inspection we can see is just VCC. And the collector saturation current, IC sat, again, that's a pretty easy one. That's just going to be VCC over RC. If you've been following along with the previous couple videos, these are pretty easy things to determine. All right, let me clear the boards here, and we're going to figure out the expression for ICQ. But first, let's think about this for a second. The current that flows from the power supply down through RC splits between the base and the collector. So the current through RC is ICQ plus IB. We're going to approximate that as just being ICQ, again, because, beta is 100 or more, so ICQ is at least 100 times IB. So that's a pretty reasonable approximation to make. Again, it's roughly the same thing as assuming that alpha is approximately equal to 1. All right, and with that in mind, let's go ahead and continue. All right, what we're going to do is Kirchhoff's voltage law from the positive rail down through RC, RF, and the base emitter junction to ground. All right, so let me fill in these voltage drops. Here we've got ICQ times RC, right? We're approximating that. Over here we're going to have IB times RF. And here we've got VBE. All right, so writing the KVL equation, working from the top through this path to ground, we get 0 equals VCC minus ICQ times RC minus IB times RF minus VBE. All right, now what I'm going to do next is collect the voltage terms VCC and VBE, put them on the left-hand side, and multiply by -1 to make things look pretty. So we end up with VCC minus VBE equals ICQ times RC plus IB times RF. All right, now to get common factors here, I'm going to make the substitution IB equals IC over beta. Right, that's one of the fundamental transistor relationships we've been using all along. And if I make that substitution, I get ICQ times RC plus IC over beta times RF. All right, and if I factor ICQ out of these two terms, I end up with ICQ times RC plus RF over beta. All right, finally, dividing both sides by the factor in parentheses, we get the equation for ICQ. So ICQ equals VCC minus VBE divided by RC plus RF over beta. All right, now that looks pretty familiar. The previous circuits we've dealt with had RE down in the denominator. Now we've got RC. Now, why did that pop down there? Well, the algebra shows why, but basically it's because we put RF in the feedback path from collector to emitter, and that changed things and ended up giving us an RC in the denominator, which is kind of cool. All right, VCEQ is simply VCC minus ICQ times RC. All right, now let me clean my messy writing out of here and drag over the nice equations so you have, something nice to look at if you want to do a screen capture or something. All right, so there we are. These are the equations we just came up with. All right, here's the circuit. All right, let's do a concrete example here. All right, we've got a 12-volt power supply, 2K in the collector, 100K R sub F. We're assuming beta is 100. Let's figure out these values. Well, VCE cutoff, that's easy. It's just 12 volts. Collector saturation current, IC sat, is 12 volts divided by 2 k ohms, which is 6 milliamps. All right, ICQ. Well, that's going to equal VCC minus VBE divided by RC plus RF over beta. So that's 12 minus 0.7 is 11.3 volts divided by 2 k ohms plus 100K divided by 100 is 1 k ohm. So we've got 11.3 volts divided by 3K, which is 3.8 milliamps. All right, so we've got 3.8 milliamps for ICQ. VCEQ is VCC minus ICQ times RC, which is 12 volts minus, not 2 milliamps, 3.8 milliamps times 2 k ohms, which works out to be about 4.4 volts. Okay, so we've got 4.4 volts. All right, now I'm going to sketch a load line here real quick, and we'll plot this Q point. All right, so VCE, IC. All right, our saturation and cutoff are 12 volts and 6 milliamps. Q point, 4.4 volts is a little more than a third of the way over, so this looks close. 4.4 volts, and ICQ is 3.8 milliamps. Okay, so there's our load line. All right, now what would happen if we got transistors at either extreme of beta, say 50 or 300? Well, we can grind through all these numbers, but to save you the pain of watching me do that, I did it ahead of time, and I'm going to drag those values over here, okay? So here's what we get. All right, if we grabbed a transistor with a beta of 50 and stuck it in this circuit, we get an ICQ of about 2.8 milliamps and a VCEQ of 6.4 volts. All right, let me throw them on here real quick. So 6.4 volts, that's about here. What the heck? All right, and if we had a beta of 300, we get 4.8 milliamps with VCE of 2.4 volts, so that's about here. All right, so this is beta equals 50, and this is beta equals 300. So we got a pretty wide excursion of beta here, a 600% spread from 50 to 300, and our ICQ changed by 170% from here to here. So it's not super bad, but it's not great. But at least we stayed in the active region, and that's an important thing. All right. Now that brings me to the next point that I want to make, and that is, it's pretty easy to design this circuit for a centered Q point. We haven't talked much about design, but this one is so easy that I figure I'll throw some design stuff in here. For an approximately centered cue point that's independent of VCC, set RF equal to beta times RC. All right, so if we had a beta of 100 and RC was 1K, we'd make RF 100K, and we should get a relatively centered cue point. All right, but I made a little note down here. For this circuit, if you've got something like a 2N3904 or 2N2222, similar transistors, and you don't actually know the beta, a good assumption for this circuit is to assume beta is about 150. All right, we'll use 100 most of the time, but for this circuit and these particular kinds of transistors, 150 is a pretty good guess. All right, so let's throw some numbers in here and do a calculation. Let's say we've got a 15 volt power supply. RC is 1K ohm, and beta is 150. All right, so what RF should we use? Well, we'd set R sub F equal to beta times RC. So that's 150 times 1K ohm, which is 150 K ohm. All right, so we'll throw a 150 K ohm resistor here, and that should give us a pretty centered cue point. Now, how do we determine that? Well, let's find IC sat. Okay, that's VCC over RC equals 15 volts divided by 1 K ohm, which is 15 milliamps. All right, so a centered load line would have ICQ equals IC sat divided by 2, which would be 7.5 milliamps. All right, that's what we would have for an exactly centered cue point on the DC load line. What do we get here? Let's see. Well, ICQ is actually equal to VCC minus VBE divided by RC plus RF over beta. Whoops. And that's so 14.3 volts divided by 1 K ohm plus 150 K divided by 150 is 1 K ohm. So we end up with 14.3 divided by 2 K ohms, which is 7.15 milliamps. All right, we wanted 7.5, we got 7.15. That's pretty close. All right, so this will always give you a pretty well-centered cue point. Not exact, but close enough for most applications. All right. And again, for the typical transistors that you'll be, using in a circuit like this, beta of 150 is probably a better approximation than 100. All right. Now, finally, I'm saving some of the fun for you guys. Okay. What I want you to do for the next time is derive the ICQ equation for this circuit. All right, it's the same thing we just did, except I threw an emitter resistor in here. All right, if you've been following along, it shouldn't be too bad to determine an ICQ equation for this circuit. All right, in fact, I think it'll be kind of fun. So, let me know what you think, and I will see you in the next video.